In this video, we're going to talk about energy. Now, thermodynamics is the study of energy transfer. And thermodynamics is essentially not just part of chemistry, but it's a part of pretty well every field of science. Thermochemistry is the study of energy transfer as it relates to chemistry, and that's kind of what we're going to be talking more about. But before we get to that, we need to go over some basics of thermodynamics. First off, there is a conservation principle in thermodynamics that is very similar to the conservation of mass principle that we learned at the very beginning of college chemistry. As you remember, conservation of mass is basically in a chemical or physical process, the total amount of mass remains constant, even though the mass may change form or identity. Conservation of energy works basically the same way. Basically, it goes in an isolated system, energy may change form, but the overall amount of energy will remain constant. Now, that's often referred to as the first law of thermodynamics. So, the first law of thermodynamics essentially is a conservation of energy principle. Of course, if we're going to conserve something, it is probably worthwhile talking about what it is we're actually conserving. So, energy is one of those words where, of course, everybody's heard the word energy, but in a scientific sense, does everyone know what we actually mean by energy? So, in the thermodynamic sense, energy has a specific definition. Energy is the ability to do work. So, that may not have helped a lot, really, because, of course, your next question is, well, what the heck is work? Well, in thermodynamics, work basically just means the motion of matter. So we have energy, which is the ability to do work, and we have work, which is the motion of matter. So essentially, energy is the ability to make matter move. Now, if you've had some basic physical sciences or what have you back in high school, you've probably heard quite a bit of what we're fixing to say. Of course, there's more than one kind of energy. Two important kinds of energy that we deal with all the time are so-called kinetic energy, which is the energy that matter has because it's in motion. And if you've had a little bit of physics, you've probably seen this formula right here. The kinetic energy is equal to 1/2 mv squared. So if you have an object moving at a certain velocity, v, and the kinetic energy of it's going to be basically dependent on the velocity and the mass. So you can use this nice little formula to calculate the energy of, say, a tennis ball flying through the air. All you have to know is how fast it's going and how much it weighs. So, the other kind of energy you've probably heard of is what they call potential energy. Potential energy is essentially the energy that matter has because it's being acted on by some sort of field of force. Now, the most obvious one that acts on pretty well everything around here is gravity. So, imagine a tennis ball sitting on a ledge. So, the tennis ball is being held up above the ground by, well, the ledge it's sitting on. And if the tennis ball were to fall off the ledge, then it would start moving because the ledge is not supporting the ball anymore. So why does the ball start moving? Well, why? Because the ball had energy to begin with. It had this potential energy because even though the ball was sitting on the ledge, the gravity was still pulling on the ball. So if we were to move the ball away from the ledge, of course, it would just fall down. And what we think would happen here is that the potential energy of the ball it had that was sitting on the ledge is going to get converted into kinetic energy as the ball starts to move. So the falling of the ball off of the ledge is actually a process that involves the transformation of one form of energy to the other. So the interesting thing is the kinetic energy the ball would get would equal the potential energy that the ball lost. So we're back to the first law of thermodynamics. Now, of course, at the moment, this doesn't sound a whole lot like a chemistry class, because everything on this current page you could have probably talked about in your physics class, and you wouldn't bat an eye about it. Of course, what kind of energy concerns us chemists? Well, we chemists are concerned with the energy that's absorbed or released during chemical reactions. And it's time to think of matter in addition to something like a tennis ball having kinetic and potential energy because you throw the tennis ball or because you can put the tennis ball in a position where it's acted on by gravity. There is actually energy stored in the tennis ball itself and in all chemicals, in the molecules and atoms that make up those chemicals. We call that energy internal energy. In thermodynamics, it's usually given the symbol U. We can sometimes refer to this as chemical energy if we like, but the thermoterm is internal energy. And essentially, this internal energy is the energy that matter has because the molecules and atoms and subatomic particles and all that are moving around, they're attracted to one another, they're repelled from one another, so you have these fields of force that exist inside atoms and molecules. You have the kinetic energy of the protons, neutrons, and electrons moving around and so forth. So all that energy makes up this internal energy, all that kinetic and potential energy of the atoms and molecules themselves. So when we do chemical reactions, sometimes we can get at this internal energy. Now, when we study energy transfer, we measure something, and the thing we measure is called heat. So in thermodynamics, heat has a specific definition, kind of like energy and work. And heat is the flow of energy from an area of high temperature to an area of low temperature. So one thing about heat is that heat is kind of by definition the movement of energy. It's a flow. Now, we use the letter Q in thermodynamics to represent heat. So, and the Q can be capital or small, just depends on who's writing it down and what they're talking about. Maybe they use a capital to distinguish one heat from another. So, get used to seeing Q as the symbol of heat. Now, the thing is, heat is a flow, so heat has a direction. And you might wonder, well, how do I talk about the direction of heat? How do I talk about the direction of the energy flow? Now, it's useful to think of heat kind of like a river or stream. And the reason I say that is that essentially the way we generally define heat is we talk about it as moving from one place to another. And the places we're going to talk about are the system and the surroundings. Now, the system you define when you're doing thermodynamics. So you specify what the system is. Of course, there are some standard useful choices that we use for chemistry. But the system is defined as the object or material that we're actually studying. So you might define a system as a chemical reaction. If you're studying the heat from a chemical reaction, you might say, okay, well, my system is my reactants and my products. If you were studying energy transfer to and from a tennis ball, you might define the system as a tennis ball. So how this is defined kind of really depends on what you want to do, what you're interested in. The surroundings, though, are everything that's not the system. So technically, the surroundings is literally everything else, but oftentimes when we're doing measurements, we treat the surroundings as if they're the immediate surroundings, the things that are right in there in contact with the system, but aren't part of the system themselves. So what we do is we say, okay, heat can basically, this energy from heat can move in one of two directions. It can move from the system to the surroundings, or it can move from the surroundings to the system. So we have two directions, and we're going back to the stream or river metaphor. In a stream or a river, you have two directions, upstream and downstream. So heat essentially has two directions, in or out. So that leads to there being two kinds of thermodynamic processes. So the first kind is called an endothermic process. An endothermic process is where energy is transferred from the surroundings to the system. Now, if you're having trouble remembering the thermodynamic terms, endothermic basically means that energy is transferred into the system. So, of course, endo sounds like in. So an endothermic process means that energy is coming into the system. Now, that's actually a gain of energy for the system, so it makes a little bit of sense that the sign of Q for a process like that, where energy is coming into the system, is positive. So an endothermic process where energy is coming into the system would have a positive sign. So if energy is coming into something, Q is positive. Now, of course, the opposite is the exothermic process, where energy is transferred from the system to surroundings. And of course, this is a nice term here because if energy is going from the system to surroundings, it is exiting the system, which sounds an awful lot like exothermic. So an exothermic process, energy exits. Now, since the system would be losing energy, then it makes a bit of sense that the sign of the heat here should be negative. So energy coming in, endothermic process, positive sign for Q. Energy going out, exothermic process, and the sign of Q is negative. Now, you might be wondering about this thing on the right here. Temperature of the surroundings. And what I've done is I went into the lab and I recorded some endothermic and exothermic reaction demonstrations. So you might wonder why there's this column that says temperature of the surroundings. I thought we were studying the system. It pretty clearly here says the system is the object or material under study. However, when you measure something, what you're usually measuring is not the system directly. You're measuring the surroundings to see what the system has done. So let's see how this actually works. Let's look at an exothermic reaction first. So I went into the lab and I recorded a demonstration of the reaction that we see up here at the top of the screen. We are going to take 3 molar hydrochloric acid at a room temperature in the lab of 21.2 degrees, and we're going to mix it with 3 molar sodium hydroxide, and we're going to watch what happens to the temperature, and then we'll come back and explain it. And by the way, the videos that we're showing here are available on the YouTube channel to watch in high definition if you like. But let's take a look at the first video. And we'll watch this and then discuss it.
In this video, we are going to look at a demonstration of an exothermic chemical reaction. Just as a review, an exothermic chemical reaction is a reaction where energy is transferred from the system, which will in this case be the reactants and products of the reaction, to the surroundings. Now, what we want to observe is what sort of temperature change we will see for an exothermic reaction. So, I have here 100 milliliters of 3 molar hydrochloric acid and 100 milliliters of 3 molar sodium hydroxide. And as you can see, if I turn the thermometer a bit, the initial temperature of my sodium hydroxide solution is room temperature, which here in the lab today is 21.2 degrees C. What I'm going to do is pour the hydrochloric acid into the sodium hydroxide and initiate a chemical reaction. A chemical reaction is the reaction between hydrochloric acid and sodium hydroxide to make sodium chloride, table salt, and water. So let's see what happens. So I'll pour the solutions together, agitate to mix the solutions up, and let's look at the thermometer again. As you can see, the temperature is rising, and it's still rising. Currently it's 38.4 degrees Celsius. Let's see how high this goes. And while we're waiting, we'll talk for a second about why the temperature would be increasing. Well, for an exothermic reaction, energy is transferred from the system to the surroundings. In this case, the system is the actual chemical reaction, but the surroundings are everything else. For example, the water energy is going to go into the water into the flask and into the flask itself. It looks like the temperature is starting to come back down. I think it peaked at 39.7 degrees C. So the temperature is going back down now, of course, because the room is much cooler than 39.7 degrees C. But we can clearly see that this reaction released energy to the surroundings. So the temperature went up because the temperature that we're measuring is actually the temperature of the surroundings. The thermometer is stuck in the water that the reactants were in. So, of course, energy that's coming out of the reactants will go to the water and to the thermometer sitting in the water. So what we see here is that for an exothermic reaction, like a reaction between hydrochloric acid and sodium hydroxide, we expect the temperature to go up because the energy is being released into where we're doing the measurement, which is the surroundings.
So, as you could see, in the exothermic process, the energy goes from the reactants and products, which is the system, to the water in the flask, the thermometer, etc., which is all the surroundings. So we saw a pretty clear temperature increase from room temperature of 21.2 degrees to a temperature of 39.7 degrees C. So the water has absorbed the energy that the system has released, and it's gone up in temperature because of it. So, when we see an endothermic process, remember, we as the observers are always part of the surroundings. So, we see a temperature increase because the energy has been transferred to where we are. Now, this acid-base reaction is, you've probably already seen it in the laboratory. So, for an endothermic reaction, you've probably seen a lot less of those. The endothermic reaction we're going to do is barium hydroxide octahydrate and ammonium nitrate goes to ammonia, water, and barium nitrate. And what we're going to see here is what happens when you do a chemical reaction where energy is absorbed from the surroundings. So we'll watch the second video here and then come back and discuss it a bit.
Octahydrate, BaOH to 8H2O, and ammonium nitrate. And as you can see, we have some of each compound here. We have 25 grams of the barium hydroxide octahydrate, and we have 12.7 grams of the ammonium nitrate, which is a stoichiometric ratio for these two compounds. And we currently have a temperature here in the lab, according to our thermometer, of 21.5 degrees Celsius. Now, before we start the reaction, let's talk about this, because you might notice that I have my two reactants here in the solid state. This is a kind of unusual reaction in that this is a reaction between ionic compounds that will actually initiate in the solid state, unlike a lot of the precipitation reactions that we've talked about in class before. So, what we're going to do is we're going to mix these two solids, and then we're going to see what the effect on the temperature is of this endothermic process. So I'm going to pour the barium hydroxide octahydrate into the ammonium nitrate flask, and we will monitor the temperature. The reaction is going to look like this. Barium hydroxide octahydrate reacts with ammonium nitrate to make ammonia, which will be a gas in this reaction, water, and barium nitrate. So, let's get started. We will pour one reactant showing the temperature appears to be dropping relatively quickly. If you look at the moment, the temperature has actually dropped below 0 degrees Celsius currently, and it's going still pretty rapidly. We're at -4 degrees C. Shake it up a little bit more. We are currently at -7.7 and still going down. So what's going on in this reaction? Well, what's happening is this process overall is endothermic. So endothermic processes absorb energy from the surroundings. So what we have is, for this reaction to proceed, we have the energy being pulled in from the thermometer, from the flask, from the substances that have already reacted. And in fact, if we touch the outside of the flask, we'll feel it's quite cold. And the temperature inside, as you can see, has dropped to -10 degrees Celsius already. So well below the freezing point of water. Now, speaking of water, you might actually be able to see certainly some condensation forming on the outside of the flask. And it's actually frozen, so it's getting so cold that water vapor from the room is condensing and freezing on the outside of the flask. So this reaction is actually still going. -15.3 degrees C so far. Doesn't really show much sign of slowing down yet. -16, still going down. But you can see this reaction really pulls in energy from the outside. So that's what an endothermic reaction will do. Now, a few other things about this reaction that are interesting. It was a solid phase reaction. One of the products is ammonia. If you were here in the lab with me at the moment, you probably would want to plug your nose, because the smell of ammonia is steadily coming out of this flask. So if anybody were to sleep in here, this would certainly wake them up. This reaction also produces water, which of course is going to form in here. First as a liquid, and some of the places in the flask you can see some of this liquid water happening. If I stir it around now, you can certainly see the liquid forming. The reason it's a liquid, even though the temperature is currently about -16.6 degrees, is that we have an effect in here going on called the freezing point depression effect. Basically, the presence of other things like the barium nitrate in the water helps lower the freezing point of the water below 0 degrees. So the water on the outside of the flask freezes. The water on the inside of the flask, because of all the other junk in there, is still liquid. So what we see here is that an endothermic reaction pulls in energy from the surroundings and causes the temperature to go down. Now, of course, the temperature is now going to slowly start going back up.
So we saw an endothermic reaction there, and it was quite obvious that energy was being pulled in from the surroundings, and in this reaction it was pulled in so rapidly that it actually caused water from the air to freeze out onto the outside of the flask. So an endothermic reaction can be spotted as a reaction that causes the temperature of the surroundings to decrease. And you might wonder, what happens to that energy? Well, what happens to the energy that the endothermic reaction is taking in is it actually becomes some of that internal energy. It's going to the atoms and molecules of the products. So we've transferred energy from the thermal energy of the surroundings into the chemical or internal energy of the products of the reaction. So hopefully now, having seen those processes, you have a little bit of a handle on the chart that we had before about the temperature of the surroundings. So exothermic reactions warm the surroundings, endothermic reactions cool the surroundings. Now, of course, we would like to measure energy transfer, or measure heat. And anything that's measurable needs to have some units. It turns out that there are quite a few units for energy, but there are two that are fairly common. I know you've heard of at least one of them before. The first unit we're going to discuss real briefly is called the calorie. Now, the calorie is actually defined based on thermal energy. It's defined as the amount of energy required to change the temperature of 1 gram of water by 1 degree Celsius, or 1 Kelvin if you're using that temperature scale. So just to get an idea of the physical size of stuff we're talking about here, so a gram is basically equivalent to a milliliter for water. So it's about the amount of energy required to change the temperature of a milliliter of water by 1 degree. Now, of course, everyone's heard of calories because they're on pretty much every food label that you would go to the grocery store and buy. So we should mention the calories in food. The calorie that's given on typical American food labels is actually the kilocalorie, which is often abbreviated kcal, or sometimes they call it the kilogram calorie. And apparently we Americans are terrified of metric prefixes. We can't just call it kcals like everyone else. So oftentimes the calorie you find on food labels is just capitalized and said. But you can rest assured that when people talk about counting calories and calorie content of food, at least in the US, they are referring, actually, when they use the word calorie, they're referring to the kilocalorie. Now, of course, what's a kilocalorie? The prefix kilo means 1,000, so there are two ways you can think about it. It's the amount of energy required to raise 1,000 grams of water by 1 degree C, or the amount of energy required to raise a kilogram of water by 1 degree C. So you can think of it as a kilogram calorie, if you like, or just 1,000 of the regular calories. So if you look at the side of your can of Coke and it says this can of Coke contains 140 calories, they are talking about 140 kilocalories. Now, the calorie is based on thermal energy, so temperature change. The other unit, which is actually, even though both of these units are metric, this second unit, the joule, is actually the SI unit for energy. And the difference between the calorie and joule is basically a difference of definition. The calorie is defined based on thermal energy. The joule is defined based on kinetic energy. And in fact, it comes right out of the kinetic energy equation. So if you remember, the kinetic energy equation is kinetic energy is equal to 1/2 mv squared. So if you put the metric base units for all those quantities in there, you put the simplest possible units, what you get is this. Mass, the actual base unit for mass in metric, is the kilogram. The simplest velocity unit you can come up with is the meter per second. And if we square it, we get meters squared over seconds squared. So if you just plug in the standard SI units for mass and velocity, you get something that looks like this, which is the kilogram meter squared per second squared. Now, people get really tired of saying kilogram meter squared per second squared, so essentially they gave it a nickname. This is what they called the joule. So the joule is simply a kilogram meter squared per second squared. Now, these units look like they've been defined completely differently. One of them is from kinetic energy, one's from thermal energy. However, they are both energy, because kinetic and thermal energies are both two different forms of the same thing. So there's a very simple relationship between the calorie and the joule. The joule is a bit smaller of a unit than the calorie, so there are 4.184 joules in every calorie. Now, since both of those are small units, typically when we start reporting heats as they relate to chemical reactions, the joule's too small, so we use the kilojoule. Kind of like the calorie is too small for food, which is basically chemical reactions, so they use the kilocalorie. So kilocalories and kilojoules. Now, one question you might wonder is, okay, well, how do you even begin to measure these things? And there are several ways you can measure energy, but what's useful to us, particularly in the chemistry lab, are the concepts of specific heat and heat capacity. Now, the specific heat, of course, is a measured quantity. It's the amount of energy required to change the temperature of 1 gram of a particular substance by 1 degree Celsius. And if that sounds strangely familiar, it's basically how they define the unit, the calorie, for water. So the amount of energy required to change 1 gram of water by 1 degree C is 1 calorie. So the specific heat of water is also 1 calorie per gram degree C. Water, basically being one of the most important substances on the planet, oftentimes ends up being our reference value. So the specific heat of water in calorie units is 1. Now, for joule units, 4.184 joules per gram degree C. So in other words, if you have a gram of water and you change it by a degree C, then the amount of energy required to do that is 4.184 joules. Now, what you can do with specific heat is you can usually use it to relate a temperature change for a chemical to a specific amount of heat. Because you would typically know the specific heat for common substances. These are tabulated, easy to find in data books, or in the modern era, just type it into Google. What is the specific heat of lead? And it'll come right up. So there's a formula. If you want to know the heat for changing the temperature of a particular amount of substance, take the mass of the substance, multiply it by the specific heat, multiply it by the temperature change, your delta T. Now remember, heat is directional. And sometimes people get confused on, okay, well, this heat I'm talking about, is it supposed to be positive or negative? You know, is heat coming in or is heat going out? If you're using the specific heat formula, I have a hint for you. In thermodynamics, things are typically defined as the difference between the final state and the initial state. So when you see something like a temperature change, it is the difference between the final temperature and the initial temperature. So when you're calculating with specific heat, take the final temperature, subtract the initial temperature. Now, what that does is it ensures you always have the right sign. For example, if you are taking something and raising its temperature, typically to get something to go up in temperature, you're going to have to put energy in, right? So you would expect the Q here to be positive. So here's how this works. If the final temperature is greater than the initial temperature, the sign of delta T is positive and Q is positive. On the other hand, what if something cools off? What if something goes from a high temperature to a low temperature? Well, the way something cools off is it releases energy. So a Q associated with that should be negative. So let's look at this again. If the final temperature is less than the initial temperature, then delta T is going to be negative, and since mass and specific heat always have to be positive, the sign of Q would be negative. So to make a long story short, if you remember that anytime you see a delta T in thermodynamics, it's final temperature minus initial temperature, then your signs for things like Q, things that are directional, will always end up being correct. Now, the specific heat is for a particular substance. That's what this S is, specific heat of a substance. You will sometimes see something called the heat capacity. And you might wonder, what's the difference between specific heat and heat capacity? Essentially, the heat capacity, instead of being for a substance, is for an object. So a tennis ball might have a heat capacity, but rubber, the substance the tennis ball is made out of, would have a specific heat. Now, if you take a look at the equation we have for heat capacity here, Q is equal to C times delta T, then what you'll see the difference is there's no mass term, because the mass term is factored in. So where might you see a heat capacity given instead of a specific heat? Well, typically you would see this for an object like a reaction vessel. So in our next video, we're actually going to talk about something called calorimetry, which is the measurement of heat. And to do that, you use a container, which usually is called a calorimeter. And if you buy a calorimeter, which is essentially an insulated container from a manufacturer, one of the things they'll do for you is they will give you the heat capacity of that calorimeter, so you don't have to worry about weighing it and figuring out what it's made out of to find out how much heat it absorbs. So instead of having to do mass and specific heat, all you have to do is use the manufacturer's specified heat capacity and whatever temperature change you had in your experiment, and it just makes your life a little bit easier. So specific heat and heat capacity are basically used for the same thing, but the difference is one of them is for a material, the other one is for an object. That's all for this video. Thanks for watching.